So moving on to isotopes now. So we said before that atoms have, or elements I should say, elements all have the same number of protons. But if we change the number of neutrons in that atom, then we get what is called an isotope. So an isotope of an element have the same number of protons, so it's still the same element, but a different number of neutrons. And that means it has a different number, a different mass number. So remember that mass number was A and the atomic number was Z. So it means that we've changed the mass of it. I have some examples down here. So since the chemical properties of an atom are determined by the number of protons, different isotopes of an element have the same chemical properties. So hydrogen 1, 2, and 3 all have the same chemical properties, just different mass numbers. So we have this different number of neutrons, and just see here how we've got this has an atomic mass number of 1 here, 2, and 3 here. So we've just added up the protons and neutrons. Helium, same deal. So we've got helium 3 and helium 4 here, and here we have lithium 6 and lithium 7. Okay, so we just added different numbers of protons to the nucleus to create that different isotope. Isotopes become very important when we talk about radioactivity. So different isotopes can be more or less stable, and we'll talk about that a bit later. So they are significant. Okay, so I have an example here. So at the moment we're just focusing on calculating the values when we have different isotopes and things like that. So we have magnesium. So we're looking at magnesium atoms have Z equals 12. So I have 12 protons. So they contain 12 protons, but the number of neutrons can vary. So we have different isotopes, so 3 different isotopes. So the symbol then, 12 down here. Oh gee, I moved out of the way. Anyway, 12 protons. Number of neutrons is also going to be 12 because our atomic number is 24, and we can call this 24 magnesium. I usually say magnesium 24, so you could write magnesium 24. This one here, we know that all of these are going to have 12 protons, so Z's always going to be 12. 13 neutrons, which means our atomic mass number is going to be 25. And it's got the symbol 25, 12 Mg, and we call it 25 magnesium. And we have 12 here. Again, that's gone up, but oh well. 12 here. The number of neutrons are going to be 14 this time. Atomic mass number is 26, and it's 26 magnesium. Cool. So thus magnesium exists in 3 different isotopic forms. Similarly, we have now example 4, hydrogen. Now, the hydrogen atoms have special names, and maybe you've heard of these before, deuterium and tritium. So we have hydrogen 1, deuterium is hydrogen 2, and tritium is hydrogen 3. Okay, so the protons are 1 in all of these. Number of neutrons for hydrogen, normal hydrogen, is 0, and we have an atomic mass number of 1. Okay, 1, 1, 2, 1, 2, 3. So remember protons here, neutrons, oops, and atomic mass number. Okay. All right, so if you look at the periodic table here, you might have noticed that they have decimal places here for the mass number. Okay, but if it's simply a matter of adding number of neutrons and number of protons, then they should just be integers, because you can't divide a neutron or a proton. Well, at least at this level, we can't do that. So we're considering a neutron, proton, and electrons like indivisible at this stage. Okay, so we have different numbers. So the way they get the decimal places in here is because the different isotopes occur naturally at different percentages. So the example here is that naturally occurring chlorine consists of 75.8% chlorine 35 and 24.2% of chlorine 37. Okay, so 24% of chlorine has 2 more atoms compared to 75.8% has 2 less if we just compare those two isotopes. So find the average mass number. So what we have to do is we say A average is going to be equal to 75%. So if we change that to a decimal, times by, it's got a mass number of 35. And we add on 0.242, so 24.2% as a decimal is this, times by 37. And we end up getting, I did this comparison earlier, let's see. So it ends up being 35.484 in our calculations. If we look at chlorine here, up here, it's got 35.45, so maybe when they calculated the period for this periodic table, they used more decimal places or something like that. I'm not sure. I'm not sure why we got a different answer than that one. But anyway, that's how they calculate it there. Okay. And we'll talk about formations of ions next time.